Wetware has been doing data mining in finance since 1997. This group started in 2011 as an extension of as a study group for the Stanford online classes in artificial intelligence and machine learning. And after the class was over, many of us decided that we should keep meeting, and it has grown and grown. I think this is something that's unique for this area. I'm not sure this could happen in any other part of the world. But thanks all for coming. We have a speaker today. I'd like to first go over some housekeeping. Our schedule, we'll start with our speaker, and then afterwards we can break up into topic sessions. There are topic sheets that we'll put out on some of the tables. Things like software packages, neural networks. You can find a topic that you're interested in, and that way you will find your nearest neighbors. So, we're recording today, so if you can try to keep the ambient noise down, it helps the signal to noise ratio. We are here for teamwork. Many of us are working on projects in machine learning. We are learning from each other and sharing with each other. Please tell people about the projects that you're working on and share freely from your own experience and knowledge. Sometimes, particularly in machine learning research, one clue into a new approach to a problem can save a month or a year of work. So it's really helpful if you will share your insights, and that's one of the biggest benefits from getting together a large group of people who have some background in this area. I'd like to thank our organizers. We have quite a few people who have been helping to make this happen. Dan Gerlang is here somewhere. He's in charge of speakers. If you're interested in speaking, or if you have a referral to somebody who you think would be a good speaker for this group, please let him. Chad Curl is in charge of sponsors. He's in the back there. If you're interested in sponsoring this group, or if you have a referral to someone who may be, please put them in touch with him. We should also thank our sponsors, Google and Betafund and HackerDuce, and Adrian Cochran, who is the executive director of HackerDuce. She's here. She's going to mention a little bit about a DARPA-sponsored hackathon that's coming up.
Hi guys, welcome to HackerDuce. Welcome back to a lot of you. So, what are we doing here at HackerDuce? We're a nonprofit. We're supported by corporations and the state of Massachusetts. What we do here is we promote the growth and the development of the technologies and the skills required to process and analyze and apply big data. So we host a lot of meetups, training events, workshops. We're always open to any events. If you guys have any ideas, things that you want to do, definitely talk to me about that. We have a few different style hackathons here, and tell you a little bit about those. The first style and how HackerDuce really started out was with big data hackathon, and I don't see a ton of those happening around here. So we provide compute power, we provide a lot of data sets, and we ask that you use specific technology or you look through a number of data sets to find correlations or just do something interesting with big data. So we have a big data hackathon coming up in July, and that one will be focused on using Storm and Finagle, if that's of interest to any of you. Definitely check out our calendar on hackerduce.org. And this video is very fitting. Today, I announced a hackathon that we're having on June 28th, different style hackathon. This is to develop a prototype of an app. Those are more common and frequent around here. But this one will be really interesting. It's the first time the Department of Defense is releasing data for a hackathon. So they're really excited about it. Yeah, that's right. It'll be a 24-hour hackathon. It'll start on a Friday evening. It will end on Saturday evening. We'll have Tony Parham, the governor's, he's the governor's innovation officer. He'll be speaking. The data set's actually not too controversial, even though it's coming from the Department of Defense. It's nutrition data. So the goal would be to develop an app for soldiers to use. They can plan their missions and they can plan what food to bring. They don't have anything like that now, so they need to know that they're going to be able to bring enough calories that they need, for their mission, and how much weight that's going to be on their backs. And so it's a brand new data set. It'll be really a lot of fun. There's cash prizes, and I encourage you to talk to me about that at the end of this event if you'd like me to get you signed up or if you have any questions about it. And I'll just mention also, we have the third style of hackathon is about analyzing data, and we hold those with Kaggle. So if you guys are familiar with that, we had one of those hackathons a few weeks ago. Some of you guys were here. It's pretty exciting. Can most accurately predict an outcome from the data set. So, so you guys might be interested in that. I'll be here all night. If you have any questions about what we're doing here, or have any ideas you want to share with me, we're always looking for new data sets, new technologies to bring in. And thanks again for coming tonight.
Thanks again, Adrian, and thanks HackerUs for hosting us. Like Dan said, I'm the other Dan Garline. I help organize the speakers for New England AI, so if you're interested in possibly giving a talk or know someone who might be interested, then definitely get in touch with me. I'd like to introduce for tonight, Mauri Niininen. I said it right, I asked him beforehand. He works as Director of Engineering at Nokia and has his Master of Science in Engineering from Helsinki University. And tonight he'll be talking about his use of probabilistic neural networks in Morse code understanding. So without further ado.
All right, thanks a lot, Dan. So before we get started here, just a quick poll. Do we have any ham radio operators in the audience? Okay, we have one. Okay, how many of you know Morse code? It will be a quiz afterwards. So. All right, well, we're setting this up, so let me set the stage. So Morse code has been around quite a while. It was invented around 1836, and so it's about 177 years old technology. And some of you may sort of wonder, why bother? Why should we, focus on something that is like dead technology? Now, in the ham radio circles, this actually is still a very relevant technology. And it's the very quick way to send messages with very minimal equipment. So you can be deserted in an island somewhere, and with a little tiny transmitter, you can call for help. So the topics that I'm going to cover today are listed here. So first of all, for those of you who don't know Morse code, I'll give you the basics, like what this is about. I'll talk about my motivation, so why do I want to solve the problem? And I want to define the problem for you. I'll cover some of the prior art. This is not a sort of new innovation. People have been trying to apply machine learning technologies to Morse code decoding at least 65 years. I found a lot of papers and studies from like 50s and 60s. Very, very advanced stuff that people have been working on. Just to set the standard, I'll explain what's the human performance level in decoding Morse code. Some of this stuff is truly amazing, like how well the brain can decode Morse code. I'll give you some numbers to set the record. And then I'll go into the problem space. So what are the problems we need to solve? And then I'll cover some of the methods that I have used in the work that I've done. I'll share some results. And then I'll discuss about the future work. So what I think we need to do to solve the problem. So the first topic is, what is Morse code? There's a couple of things that that you need to know. So Morse code is basically a way to encode letters or characters in a pulse of series of pulses, short and long pulses. So we call these pulses like dits and dars, or dots and dashes. So if you have a sequence of dits and dashes, or dots and dashes, that kind of encodes a character. In this particular case here, we have the letter A. There's a couple things that you need to know. So the encoding is done by duration. So dit typically is like a unit of 1, and the duration of the da is 3 times dit. And then there's a pause in between. The pause is supposed to be 1 dit length. So that's kind of the basic rule. The space between two characters is 3 dits. The space between two words is 7 dits. So with these basic rules, it should be relatively simple to figure out how to encode and decode multiple, right? How many of you have ever written like a Morse code decoder software? It's like computer science, 101. It's like the basic problem. Just for fun, one of my colleagues was learning Ruby language, and so on Sunday I decided I need to learn Ruby. So I went to the Barnes and Nobles, bought like 5 Ruby books, and I wrote Morse code decoder in the afternoon. So this particular program, it reads like a WAV file from the hard disk, does a Fourier transformation, looks at the signal, calculates the dits and dars, and then outputs a character. Very simple program. It's about this much Ruby code. Simple problem, right? So let's listen. How these things sound. So I have. Anybody can decode that? Is it you? Okay, so we have one person who was able to decode that. Okay, how about this one? How many of you think that there's Morse code in there? How many of you think that there's no Morse code? It's just noise. Okay. So the difference is 17 decibels. So the first sample was 0 dB, so there's equal amount of signal versus noise. The latter example was there was 17 dB more noise than signal. So the signal was really like 30 under the noise. So this is one of the problems why decoding Morse code is difficult. Usually when you get the real Morse code, you listen to radios and stuff like that, there's always noise. So noise is one of the big challenges in Morse code. So let me talk about. Okay. So as Dan introduced, I studied in Helsinki University of Technology. I was in a lab that Professor Teuvo Kohonen was leading. I don't know if anybody knows here, Dr. Kohonen. Self-organizing maps, familiar? Okay, so Kohonen was the guy who invented self-organizing maps, and I was a student in his lab back in the early days. So at that time, computers were pretty low-powered. So in 1977, I built this little single-board computer. Had magnificent amount of RAM, like 2 kilobytes of RAM and 1.75 megahertz CPU. And I wrote with machine language a simple Morse code decoder program for this computer. And of course, it didn't work. It didn't work well. It decoded, but a little bit noise and boom, it didn't work. Now, go forward 35 years, computers are quite a lot more powerful. So I built last year a new desktop computer. This one had 16 gigabytes of RAM and the latest Intel i7 CPU. So there's definitely more horsepower available these days to apply much more complex algorithms to sort of do the Morse code decoding. So I have hope, maybe we can solve the problem if you apply a little bit more sort of horsepower and algorithms. Now, as I mentioned, this is not a new problem. People have been working on this problem at least 65 years. So some of this stuff that you see on the screen there, they have been like really smart people focused on this. I found at least like one PhD study, one person who did his master's and PhD on the problem of how to decode hand-sent Morse code, how to apply machine learning algorithms to solve that problem. In the 60s and 70s, when the US was in war in Vietnam, there was a shortage of trained operators, radio telegraph operators, people who know how to decode Morse code in their head. And a lot of money was poured into this research. They applied the latest computers and tried to basically automate the job of, getting the messages, transcribing them, and so on. So it's not lack of money why we haven't solved the problem yet. Since the Vietnam War, a lot of hand radio operators have sort of tried to address the same problem. So there has been at least, few tens of software packages. There's just a short list that I show here. People have written software to decode Morse code. I've tried most of the ones that are listed over here. In ideal conditions with a little bit of noise, they kind of work. But as soon as you have a little bit more difficult conditions, noise, interference, etc., they stop working. So decoding goes down very quickly. There's one piece of software called CW Skimmer. This software is actually pretty good. So it can decode up to like 700 signals simultaneously. It applies Bayesian logic and it works quite well, but unfortunately it's not open source. So I would love to go to the inside of that software and see how it's actually done, but it's a commercial software. So I did pay $100 for that and it works, but I didn't learn much. So what I have been focusing is a software called FLDigi. So FLDigi is a fully open source software. Everybody can go and download the source code. It runs on Linux, Macs, and PC, so all platforms supported. There's a very active support group that is very responsive, and if you have any problem with that, you are guaranteed to get a response in a few hours, because there's hundreds and hundreds of people who are on this support group. I'll give you more details later on that. So I basically took that open source software. It's pretty comprehensive. It supports not just Morse code, but up to like 30 different digital communication modes. Whether you want to do PSK31 or MFK or the old RTTY, or there's at least like 30 different modes, digital communication modes supported. So I was interested in how the Morse code decoder works. So I took that software and basically ripped the Morse code decoder piece apart. Now, before we go into the details how it works, I'll give you some details about human performance. So, how many of you send text messages? Okay. So, who thinks that sending text messages is a quick way to communicate? All right. So, I'll show you a little video clip by Jay Lennon.
I work in Morse with mail processor, primary residential. All right.
Okay, we have a problem.
must be very lucky.
Oh, yeah.
Do you have a cell phone? Do you have a cell phone?
Yeah.
And I imagine your business text messaging is a huge part.
Yes.
I'll show you what we're going to play. We found the fastest text messenger in the country. Let's bring him on. Ben Cook and his friend Jason. Let's bring him on. Hi, Ben. Hello. And thanks for dressing for the show, fellas. Ben, tell us about your record.
I typed a 160-character message in 57 seconds. Very quick.
And you accepted the message, is that correct?
Yes.
So you don't really need money.
It can be tough sometimes, but
Now let's see just how fast this technology is. Let's bring out Ken Miller and Chip Marjoley. Come on out here, fellas. My guess by the way they dress. You see, Ken and Chip, they are two Morse code operators. You know what Morse code is?
Oh, yeah?
How long you guys been doing Morse code?
38 years.
43 years in ham radio.
43 years of ham radio. Okay. We're going to get each team a card with the same sentence on it. Who do you think will be the fastest to get the message to their partner? Morse code or text message?
So, this is
Text message.
Do you think text message?
Oh, yeah.
How old is Morse code?
170 years.
170 years. Okay. All right, gentlemen, let's sit down at our desks. Okay. Now, in front of you is a card. Don't turn it over just yet. They both have the same sentence on it. When I say ready, set, go, when I say go, flip over your card and send the message to your partner at the other desk. Okay? Ready, set, go! Yell out as soon as you have the message and then read me the message. You can give it Morse code. Can you read it?
Yes, I can.
All right, second. Yes, less than second. See who's
I just saved a bunch of money on my card.
Jason, I'm sorry you're beat by 140-year-old Sorry, you also lost, but we have a consolation prize. The same crappy prize is not going to be won. You like Thai food?
I love
This is the Chandaka Thai restaurant. It's the best Thai food for like actually the only Thai food.
all right. So hopefully that gave you a little introduction of it's a pretty efficient way to send short messages. Much more efficient than text messages and stuff like that. So some people actually take Morse code to the extreme. So there are a couple guys in Germany, in all countries that are trying to push the limits on how quickly people can actually decode Morse code. So there's two guys actually who have broken the record, 1,000 characters per minute. 1,000 characters per minute. So that's 200 words per minute. Now, for the hands here, I'll play a little sound. Let's see if you can go this way. You get that?
That's faster than 4G.
So the first is Paris, P-A-R-I-S, Paris. 1,000 characters per minute. So some people actually have the skill of copying at that speed. Okay? Don't ask me why, but some people actually do this. So because this is so efficient way to send short messages, there's obviously some people who like to do this for fun. There's worldwide contests for this kind of sport, radio sport. One of the contests happens to be CPU Worldwide DX contest, happens every year. And I happen to know some of the guys who are kind of pushing the limits in this one. So there's a contestation. The call sign is CR2X. And I was corresponding with the two guys who were doing the contest last year. And so they made, in 46.8 hours, they made 7,209 contests. Just to put this in perspective, you sit in front of the radios, 2 days, almost 48 hours, non-stop. You make these two-way contacts with random people around the world at about every 20 seconds, non-stop. And so there's thousands of people who participate, and every contact is basically put in the log file. So they type in who was the call sign that they had contact with, what was the message, what was the signal report. All these log files get collected, they will be sent to the organizer of this contest, and then the logs will be compared to each other, and then the winner is sort of declared. So they check basically all these contacts with the computer logs. Now, particular guy that I was corresponding with, so he, as said, made 7,209 contacts and in roughly 48 hours. And he made 26 errors. That's 0.4% error. So I looked at the log file and I looked like what was a typical error. Out of this text string that they exchanged, he missed double bits or 1 bit. And 1 bit is roughly 35 to 45 milliseconds. Let's think about this. You listen non-stop for 48 hours, you miss like a 35 millisecond hit during that period. And we do that error like 26 times. So that's kind of the human performance level. Here's the kicker. Guess what was his score in this competition? He was number 19. The winner had over 600 more contacts and less errors. So just to give you an idea of how this sounds like, I'll play this to a bit. There's a lot of errors that happens, and there are 3 different domains that these errors are coming from. One of the errors, one of the domains is amplitude. So as you heard, the signal strength, the volume of that signal goes up and down, and that's due to the radio propagation. There's this thing called allosteric fading. I'll explain it later what that means. That sort of affects the signal strength. So that makes it difficult to sort of decode. The other piece is the signal to noise ratio. Hopefully, I gave you an example like 0 dB, minus 17 dB. It's pretty hard to decode when you have like minus 17 dB signal to noise ratio. Even humans can barely hear it. The second domain of problems comes with frequency. So if you have a lot of stations and they are jam-packed close to each other, they interfere. So you have like 10 stations within like 1 kilohertz, and you're guaranteed to get some interference. They basically jump on each other. Zero feedback is. So when you send, the expectation is that you're supposed to respond roughly at the same frequency, so that you are within the filter bandwidth of the receiver. Sometimes people do a poor job in feeding the zero feed, so they are like either up or below the frequency that they're sending, which makes it hard to go right. Frequency stability. Some of the older transmitters, they go up and down, so you can actually hear how the frequencies of changes as people are transmitting. Then we have something called the Decoder effect. Now, some of the ham operators actually use satellites, so they communicate using ham radio satellites that are orbiting the Earth. And in satellites, because they're moving so fast, there's some Decoder effect that computers may have difficult time to track. So the signal basically drifts depending on the speed and direction of the satellite, and so the computer may have difficulties tracking. The other piece the other example is some hands radio operators actually they use moon to bounce the signals. So you have some guys that transmit in bounces off the moon, and then you receive it. And as moon moves in the orbit, there's quite significant Doppler effect, especially the sort of UHF frequencies or microwave frequencies. The third domain of problems comes from timing. So you already heard, hopefully from the video introduction, that people have very different styles of sending Morse code. Many people who send manually, they have different rhythm. And computers have hard time sort of understanding the rhythm, and especially the variance in rhythm. The other thing is speed change. So within like one message, if you change your speed, first you send the call sign, and then you send report very quickly. Computers have difficult time sort of following the speed, because it's all about ratios, 1 to 3 ratio. Computers have to be very adaptable to that. And then the final piece is human errors. Humans do make errors. So as people send, they miss some dits or das, and that makes it difficult for recipient to understand what was actually being said. So let me see if I can get this to be running here. The video is not showing. Let's see.
You have to use it.
Oh, yeah. Slide goes about the So what's happening here is there's a picture of the units, or how units changes over time. So on the vertical axis, you have a height, from the ground up into space. You can see like 200 kilometers, 400 kilometers, etc. On the other axis, we have frequency. So this is how radio waves reflect or refract back from the ionosphere, and it changes. This clip is 24 hours, so you see minute by minute how it changes, how the propagation changes, how the layers in the ionosphere change. The lowest layers, they're called a D layer. That's the closest one. Then there's E layer, and then there's 3 different F layers, like F1, F2, and F3 layers. The reason for these layers is the radiation that comes from the sun. So sun is emitting ultraviolet and soft X-ray radiation. When it interacts with the upper atmosphere, it creates these layers that then reflect the radio waves. Okay. So why does this matter? If you think about over the horizon, on the horizon communication, like if I want to make a contact to Europe, what happens is the radio wave bounces off from these layers, and then it bounces from the ocean, and it bounces back to this layer, and then it comes to the recipient. As the reflective layer changes over time, as you have seen the video, you know, the timing changes. So you have multiple paths that the signal takes, and at the recipient end, sometimes these waves they sort of amplify, sometimes they totally zero each other. So that's why the amplitude goes up and down all the time, and it basically goes in the rhythm of sure. Okay.
5-minute pizza break, so
It's kind of cool that, you know, out of nowhere we came up with this good improvement. So the second improvement was to use the neural network methods on the decoding. So I mentioned earlier that I studied in Professor Teuvo Kohonen's lab in Helsinki. And Kohonen is famous on this self-organizing map, the SOM algorithm. If you haven't heard about that, you know, please Google. It's a pretty cool algorithm. So what I did was I collected about 10,000 samples of Morse code letters. Like, you know, I broke the signal into letters and then run them in a file. And I used the SOM algorithm to train out of this data. I used like different SOM sizes to train whether this algorithm could learn Morse code just from the data, you know, without any help. Can it figure out like which is dit and which is da, and you know, if there's some noise, it doesn't really matter. Surprisingly, SOM algorithm worked really well. So I was like blown away. You know, I had 10,000 samples, and I looked at where it mapped like different letters. The way this algorithm works, that if you have a pattern and you have another pattern and they have something in common, they're like topologically close to each other. Like in this case, we have the letter W, which is dit da da, and then we have the letter P, which is dit da da dit. So there's like one dit difference, and the algorithm basically mapped those two letters next to each other in this self-organizing map. So as I studied this a little bit more, I realized that the weight factors, you know, the WIG on the diagram over there, they actually look very much like a Morse code book. So I spent all this time and effort sort of creating this corpus of letters, trying the decoder, and then the end result was that, you know, it generated like a Morse code book out of nothing. So then I realized that actually you don't need the whole algorithm. You just need the piece that sort of matches the incoming pattern to a code book. And that is part of the algorithm. It's called best matching unit algorithm. So what, in essence, what is happening is you have this vector coming in, and you calculate like Euclidean distance of the code book, which we know, dit da or dit da da dit. You calculate the Euclidean distance of the incoming pattern and then the code book, and then look what's the minimum, like where's the error minimum, and that's the letter that matches the best. So this kind of like a fuzzy magic that eliminates a lot of this dependency to noise, a lot of the dependency, timing dependencies that you are dealing with when you're dealing with real signals. So it actually worked, and it worked pretty well. So these two things are now baked into the current release of FLTG. So if you go and download FLTG source code, you can see these two algorithms sort of baked. However, it's not perfect. You know, we are not yet at 99.6 sort of recognition rate. So I've been working further on this problem. So I already showed you this CW skimmer. This is the commercial software that is able to decode like 700 simultaneous Morse code signals. So I was trading some emails with the author of that software package, Alex. He's living in Canada. And he gave me some hints like how this works. You know, he didn't like open the kimono and tell me everything, but he said that you should use something called a Bayesian approach. I've never heard Bayesian before, so I had to like redo my probability theory lessons. I studied that like 25 years ago, so I had no clue. So anyway, what the Bayesian framework is about is how do you apply conditional probabilities. And in this particular case, the conditional probabilities are about the timing. So if we have a dit, and then we have a space in between, and then we have a da. And we'd be sure that that was a dit, or maybe it was a short da. Or the space in between, was that like a character space? Or what was it, a word space? So we're dealing with probabilities. So in essence, if you think about these numbers not as numbers, but you think about them as probabilities, then you can apply the Bayesian theorem, and you can calculate all this stuff as probabilities. And as you sort of move up in the stack, you know, you have stuff coming in, probabilities. Is this a signal? Is this noise? Was this a dit? Was this a space? Was it like a long space? Was it a dot? You can build a system that learns. Basically, from incoming signals, it keeps track of what did I hear, and it updates the probabilities. Allows you to sort of adapt to whatever you heard. So I built another version of the Morse decoder using this approach, and it actually worked. The challenge, however, was that it worked too well. So as I had some noise in the signal, it learned the noise. And it started to decode targets. So this was not exactly what I wanted. So the next step was, you know, I was once again corresponding with some other hams. You know, there's a lot of hams actually interested in this stuff. So I was corresponding with another ham, Dave. He's based in California, and he has some experience in probabilistic neural networks. Just for background, probabilistic neural networks are used in missile systems. You have a missile that is kind of searching for target. It sees 10 potential targets. It needs to classify which of these targets are the one that I'm going to hit. And it has to do this in real time. Missile systems, you don't have many milliseconds to make that decision, like is this real or is this not real. So probabilistic neural networks, they have some very good properties. You know, first of all, they're fast. You know, there's like one batch learning. You don't need to like train them with thousands of samples. They learn immediately. They're also guaranteed to converge to optimal classifier as they get more of these samples. So if the training set basically increases, it will converge to optimal solution. So this is the equation that we're calculating here. And in this case, you can think of these dits and das as a probability surface, the green pattern over there. We have like the dits, and we have the dars, and then we have the spaces in between. And there's like a probability curve. We're trying to figure out, the stuff that we just received, where does it fit in this surface? So what I did, first I did this in actually Excel, Excel sheet, just to verify this works. Then I wrote like octal version of this to make like some real cases. And then I implemented this in C++, and I plugged it in to this FLDG decoder. In my particular case, what I did was I had like two incoming signals, mark and space. So the mark is the duration of the signal, of what we think is a signal. Space is the duration of the non-signal, space. So two numbers coming in. I had two samples, examples of mark and space, and I had basically several classes. I created like 6 different classes. What this thing does is we have this stream of data coming in real time, and it classifies the dits and das into different classes. Usually this algorithm. And basically, that's the pattern layer. This is where it matches the incoming vector to the training set. Then it has the summation layer, so it calculates the probabilities across the stuff that you see, and then it makes a decision, which one of these patterns match better or best to the incoming signal. So it's a very simple algorithm actually. It's about 10 lines of code. Really easy and simple to implement. And here are the results. So you see the classes with different colors here. So S0, S1, S2, etc. The scale here is like mark. This is the signal, and the other one is the space. The space in between the signals. And the units are in terms of like dit units. So 0.1 represents like a standardized, normalized dit. You can see that like the red pattern and the green pattern. Red is like dits, green is like das. But then you see this other dimension, which is the space in between the characters. And it's quite random. So this represents roughly 10 minutes of Morse code taken from real signals out of the radio. I ran several experiments with this, and the best I got was about 90% accuracy. So it was able to do the decoding with about 10% error rate with fairly noisy signals. I didn't measure the signal-to-noise ratio because it was like real signal. It was not generated, computer-generated signal, but it was pretty noisy signal. So I was pretty pleased. You can see that there's clearly clusters. It's able to figure out which cluster belongs to which class, and basically allows us to decode the Morse code in a pretty accurate manner. The next steps here, stuff that I'm currently struggling with is, so how do I take this data and apply some logic on this data? So there's a couple of methods that you can use. So I've been looking at something called Viterbi algorithm. Some of you may know about that. The other algorithm that I have looked at is hidden Markov model. So basically calculating the forward and backward probabilities, so trying to figure out what's the best match of the sequence of symbols that I've seen so far. These symbols are represented by probabilities, so basically it comes back to the probability calculation. So that's where I'm at currently. So roughly 1 year, few hours every now and then on work, and then bouncing ideas between different people. Now, if you're interested, FLDG I said, free of charge open source program. Dave Freeze, W1HKJ, is leading the development of this package. I have a tiny bit of this package that I was contributing. This works on Windows, Mac, and Linux. You can go to w1hkj.com and look for the download page, and all the source code, everything is available there. There's also a Linux ham group in Yahoo, so there's the URL for that. But there's a lot of discussion about the software and how to make it better, and also if you have difficulties installing it or detecting some real signals, these guys are very helpful. So, I've spent more time than I anticipated. The summary is that, you know, there's no question, humans are much better in decoding Morse code than computers. There's like no doubt about that in my mind. But this is a great field to test different algorithms. There's a lot of data available, you know, audio signals. It's easy to generate Morse code. You have a lot of source code available, you know, that you can look and learn by doing. So I've learned a lot during this year. And what I have discovered is that these machine learning or artificial intelligence methods, they do reduce decoder errors significantly. So I think there's hope. You know, after 35 years that I've been looking at this, I think we have made some progress. So there's more details. I have a blog. Documented a lot of this stuff in my blog, so if you're interested, I guess we'll share the slides so you can go and look. And that's pretty much it, so thanks for your attention.
We don't get kicked out of our space here like we do when we're meeting over at the Google offices. So we do have time. If you have some questions, feel free to ask, and then we can mingle and talk about the topics around this.
Perfect. You're doing all your analysis except the filter in the time domain. Have you looked at the frequency domain or using other ways of transforming the frequency domain and just doing analysis there?
So the question was, like in which domain I do the analysis? Is it frequency domain or time domain? Or
You're doing it all the time domain. Yeah. Right. And was it using the frequency domain and got results?
Yeah, so I actually looked both domains. So like the first step here, when you get the incoming audio signal, obviously you need to do Fourier transformation to extract like the particular frequency where the Morse code is happening. Now after the Fourier transformation, you get this, you know, sequence of pulses. And that's basically in time domain. Now I have looked also possibility to use something called wavelets. And in wavelets, there's a couple benefits using wavelets. So first of all, as I explained, the Fourier transformation, it depends on the length of the FFT. There's a trade-off. If you have a short FFT, the time resolution really good. You get like millisecond resolution if you have very short FFT, but then your frequency resolution sucks. If you have very long FFT, you know, great frequency resolution, but then the time domain resolution sucks. Now wavelets have a property that allows you to sort of have a better resolution time-wise and frequency-wise. You don't have to make that compromise. So I looked at using wavelets to extract more information, like where the signal starts and where it ends. But I haven't implemented that yet in C++, so I only have like opt-out implementation of wavelets currently. And it's documented in my blog.
After the PMC solution, we find out that you need two new solutions to help you progress more. I didn't quite catch those two solutions and why we use those.
Okay, so the question was after PNN, like what's the next step? You know, why determine why hidden Markov models? So we basically have transformed audio signals into sequence of symbols, and symbols that have probabilities. And this is kind of the domain where there's already existing algorithms machine learning algorithms or AI algorithms that work very well. So bit therapy is one of those algorithms. It's well known. I think it was invented around like 1965. And actually, if you have a cell phone, pretty much all the cell phones in the world, they use a bit therapy algorithm to detect the incoming signals. So it's a well-known entity and people know how to use it. The difficulty that I have with bit therapy is how to apply bit therapy algorithm to Morse code. The challenge there is it's really there's no reference it's not like timing signal in Morse code. So where do you get like the basis for bit therapy? And I've tried to sort of think around that, but I haven't figured out yet like how to apply it in an efficient manner. The second option would be hidden Markov models. And hidden Markov models, they're used in like speech detection or speech decoding. And they're very good in like dealing with discontinuities and probabilities and variance in timing. Like human speech, people speak at different rates, and HMM is like a standard technique that you use in speech recognition. So HMM would be another good candidate to figure out how to deal with this variance, the rhythm changes and stuff like that. A good way yet to implement HMM. And because I'm doing this development partially in Octave and partially in C++, it's kind of difficult to cross those domains. C++ requires a lot more like time to write the algorithms. So that's kind of where I'm stuck a little bit at the moment with that problem. But I think there is an opportunity to improve using those algorithms even further.
Do pre-processing or normalization in your training set, if you could standardize a certain kind, certain speed at which characters arrive to get better results, or is it cheating to normalize everything based on what you know ahead of time?
It's kind of cheating because in real life you don't know. It varies a lot and it varies by different solutions. So if you really want to do this in real life,
your training set is the super fast Morse code operators and the slow and everything in between.
Yeah. So the challenge with the timing is not really like to detect how fast it is. The algorithm that is already baked in kind of figures the speed with a few samples. So once you get a dit and da, you can calculate the average speed, and then you can apply like some filtering to sort of adjust the speed. So speed is not the problem, but if you have rapid speed variations, like somebody sends at 25 words per minute, and then they jump to 50 words per minute, and this happens within like few dits. I haven't figured out a filter that would be able to deal with that variation without sort of missing a beat. So that's kind of the challenge. And people do that. They do change the speed in the middle of making a comment.
I was wondering if you're able to make any assumptions about the message being decoded. For example, can you assume that the message being decoded is grammatically correct English or something close to it, or are you just assuming it's random characters? I'm sort of thinking of the example of speech recognition programs. I mean, those work by making assumptions that the code text is English and then use a grammatical model of English under the surface. Are you able to do anything similar for Morse code translation?
You could absolutely use the context more, and on this Bayesian stuff, the stuff that I showed over here, I actually, part of the algorithm that I built was to take into account the English distribution of letters. So like letter E is the most common letter in English language, so the probability that, if we hear something, it looks like a dit or da, and the probability is like 0.35 versus 0.4. Then you can apply that logic and figure out that it's likely that this letter was, if it's English language, it's this. And then of course you can use the same logic for words as well. So if you have a dictionary of words, you know the frequency of the word. And in ham radio, people use a lot of acronyms, like in text messaging, you use like LOL or stuff like that. So you can apply those principles in the decoding process, and it probably will improve the results. I just haven't had enough time to focus on that problem yet.
Is there a corpus of ham radio decoding?
So there is a corpus of ham radio acronyms. There's actually several different places. I have like a list of websites where you can.
I mean actual transcripts of conversations.
So that's the question.
Otherwise you would get it.
Right. So there's I don't know any site that would have like, audio files and then the full transcript of that audio file. But we do have websites where people have recordings of these competitions, and then there's like a log, what happened during that time period. So the log basically contains the call sign of what we heard, the signal report that was exchanged, and some other like sequence number or something like that. So there are resources like that available. So if you have a little bit of logic on top of the decoding process, you would actually have a training set and test set, and then not fully complete, but like structured transcript of what happened in those two audio files. So there's stuff like that available if you are thinking of building some training model or something like that.
So it's more about the corpus of the natural use. Is it the competition with the abnormal use?
I'm not aware of one, but it would be interesting to have one. Actually, it would help a lot if you have something like that developed. Yeah.
So, on the transmission side, do any ham operators use software that takes your code and output Morse code, and the person who sees the transmitter is Morse code?
So most of these people who do the competition, big time competitions, they don't give Morse code by hand. They use computers to output. And there are some specific contest programs where you only need to write what you heard, like the station's call sign, and then the computer does the rest. It sends, the response, it sends the signal report, it sends the sequence numbers, all that automatically. So it's all computer generated Morse code. And even to the degree that it tries to compress the time, so the call sign will be sent at certain speed, and then the standard thing that everybody kind of gets, because it's standard, that's compressed in time. That's why you have these speed variations. So people do use computers to send, but the challenge is that the receiver end, the decoding end, has not progressed as much as the sending end. And because of these challenges with noise, with variation, with the stuff that I listed here, it's a pretty tough problem to solve. There's no simple ways to get the recipient of the decoding part correct.
Is anybody looking at this data and trying to identify individual from the election areas rather than looking at the regular part, looking at the personal differences that I can do an operator identification?
So I have not heard that somebody would have, but it would be a great little project to build a database of signatures. So this operator, his style is this, and you can sort of characterize with a couple of parameters, like have a model of how it sounds. But I haven't heard anybody doing that yet. It would be a great tool.
I assume as human you can sort of do that.
With human, you can recognize. You go to 7 megahertz band at this time of the day, and you go 7.065 megahertz, and you will hear some individuals, and you need to listen 2 seconds, and you know exactly who is standing there. So people do have very characteristic signature, but I don't know any computer software that could do that same thing.
Your first slide was that your software? Is it decoding that? Sure.
how it looks real life. So listing the microphone on the computer. So that would be something. As you can see, computer had very difficult time sort of listening to the audio coming from the loudspeakers, all the echoes in this room, and trying to sort of make sense out of the stuff that is coming through the microphone here. So it's not very easy, but this is how it works. So basically, the spectrum is the moving part here. As I speak, you can see the spectrum of my speech. Different sounds making different frequencies. So 0 frequencies down on that end, and we have 1500 hertz over here. And what the computer does is it looks at the area that is marked with red. That's the filter. It looks only those frequencies and tries to make sense of, like, what do I hear? Do I hear noise? Do I hear signals? What kind of rhythm I have, and tries to do the decoding in real time. That's how it looks in real. And you can go and download the software yourself and play with it, so it's really neat. It can also generate Morse code, so if you want to create stuff yourself,